We'll continue on the example we had last week, which is the place equation, plus or plus place. So I'm going to continue on the example. So first, the equation we want to solve is del squared 0 or x plus y 0. Next, constructed a grid. Solve this equation on of 9 inner nodes. 1, 2, 3, 4, 9. Enter them. P1, 2, P3, 4, 6. So I'll repeat some of this. Try to solve it numerically in different 9. Yeah. We also have some boundary conditions along the y and x axis. Outer points. You have to solve the Laplace equation for these nodes, since we're already given the boundary conditions. So we will define the boundary conditions this line as T, so G top. This line right for on the right side, and the left bottom. So also we define that y-axis goes from 0 to 0.5, the x-axis 0, 0, 5, x 0, 5, and y from 0 to 0.5. The left boundary condition is just zeros, bottom is zeros. L, E, zeros. You see there's a lot to define before we can actually start. Okay, g of t of x of y 200x and of r y is good y. So okay, and then you remember that we try to discretize these. Yeah, more details also. The grid spacing in both x and y is h. This direction, this direction. Then I think we should have everything solve this problem numerically. In our case, grid spacing h is eighth. Have 1/8, 1/8, 1/8, eighth. That makes 4/8, which is a half. Then we have the whole thing here. Okay, and then we have the discretized version. I will number all of the nodes in x. The counter there is I, and the counter in y is j. What's this usually used? Counter in x or on x nodes. I, it can be whatever, and j. Okay, so then we have to figure out the discretized version of this. Last time it was y I 1 j plus y I minus 1 j I j plus 1 I j minus 1 minus 4 I j equals 0. That's the discretized version of the Laplace equation. Next, we can solve for each of these points. So I'm going to do some of them again, but a bit quicker this time. So if you want to look what P1 is supposed to be, well, we looked at this equation. Okay, here. Stencil as well. J is there. I, 1, counter of x. J, 1, J, I, because x point, J minus 1. I hope that's known from last week. Actually, last week I maybe have a, or there, just illustrate the full equation. So that's the full equation. Without the 4, it's just the numbering of the nodes. There's a lot to keep hammering here. Okay, then it's easy to start. So P1, if you want to figure out what this point is supposed to be, we need a value of this point, this point, this point, cross around it. For P1, we have, well, we need a point 2, plus that ui plus 1. 2, need I minus 1. That is going to be our point here, GL. GL is only 0. 0. We also need here, so now 2. There. So the top one, top of 1/8, 4/8, or a half. This point, y is a half or 4/8. So just having everything in eighths, or I hope simplicity. Plus, well, the last one we need is 4 down here. 4, and according to the last equation, this should be 0. If we do the same for, well, got something, and minus 4 of P. It's 0. Then we can solve this equation. If we for 2 going to be, oh, I can see, so 2, then we need this one here, and this one there. 1 plus three eighths, eighths plus P5. 4 of GT, of course, plus okay, and then we have 9 of these. We can form a matrix. Solve. So I'll stop there. Yes? Yeah. Oh yeah. I was thinking since you already had this yesterday. No, last week. So for P2. So okay, so I should perfectly clear. I can switch. Okay, so I'm just solving this equation. That's the discretized version of the Laplace equation over here. So I'm looking at solving P2. Well, P2, then I need I plus 1. So I plus 1 standing in P2 is going to be at this point. And then minus 1 is P1. Then the next one is ij plus 1. That's the one above it. Then you get the P. Then the one below it is P5. That's this. Then you have the point itself. 4 of those. Okay, 9 of these. So I won't go through all of those because they are similar and yeah, they're similar. It's just going to take a while. So if we can just gather all of these points, even though it looks like a matrix here, we're going to gather them in a vector. We'll create a vector P of all the points. P1, 2, 3, 4, 5, 6, 7, 9. So, and then we have a matrix A, which is all of these front of, well, these, and then this equal to. What I'm trying to do now is get this equation, or actually this equation for this system over on the form AX equals B. A, or A, where P is the unknowns, or X's. We have all of the points here. A is just the weights, and B is determined by the boundary conditions we have. So we'll do the easy part first. So B, this is defined by the, again, boundary conditions. And we see there's a system here. So the first elements of B will be, we receive P1 as g of t evaluated at this point, then P2 evaluated at this point, and for P3, you are going to use GT, and GR. Then you have both of them. And then for P4, you won't have anything. Well, the boundary conditions is just going to be 0, so B is also 0. So P1, so GT evaluated at this point is going to be 25. Switch it over to right-hand side. The sign changes, so it's minus. We have g of t evaluated at 4 eighths, minus, or 50, other side, 50. Then for P3, well, the contribution from the top will be 75. Contribution from this point will be also 75 minus 150. And then for the next ones, 0, 0, those are for 4. At this point over here, 0, P5, you don't have any boundary conditions there. There's also just going to be 0, P6. Want to evaluate boundary condition only there. Evaluates to 50 sides, minus 50 for P8, no P7 and 8. Well, this is 0, this is 0, 8, this is also 0, so 0 and 0. And for P9, we need to evaluate this boundary. Minus 5. Okay, so unknowns, boundary conditions. Then we need to weigh off this with regards to other. So that's the A matrix. Well, looking at P1, we see that we have going to be, here this is going to be minus 4 of P1. First one, how many P2s do we have? That's 1. How many P3s? 0. And then we have 1, 4. And then the rest is just going to be zeros. For 2, see that we have 1, P1. For 2 itself, we have minus 4 of those. And how many P3s do we have? 1. Zero of 4s and 1 P5. So, and then without writing the equation, we can look at the equation for P3. Well, see that we have one of these, 1 P2, and 1 P6, and then nothing else, except P3 itself. And we have 0 of 1, 0 of 2, no, 1 P2, don't we? Yeah, 1 P2. For P3, we have no P4s, or all the way over here, no P5s, but a 6. 0, 1, 2, 3, 4, 5, I said? No, 6. Yeah, that makes sense. Okay, and we can continue. So for this next point, for 4, we have, well, P1, P2, 5. One, let's say P2. 4, nope. P1 here, then we have 0, 2s, 0, 3s. So if you look at this. So instead of me walking back and forth, I'm going to use my note. So P4, if you look at this point and you see of all the neighboring points, we see that we have 1 P1, we have 0 P2s, 0 P3s far away, and we have 1, 2, 3, 4 itself, and then 1, 5, 0 P6, and 1, 7. No. Yeah, because so if you just imagine all of these crosses, then figure out what you want. Okay, and then for P5, we see that we have 0 of P1s, 1 P2, 3s, 1 P4 minus 4 P5, 1 P6, 0 P7, 8, 0 P9. And like, maybe we should just both of them. So for P6, we have 0, 0, 1, 0 4s, 1 P5, minus 4 P6, 0 P7, 8, 6, 9 over there. And then we might see a repeating pattern here. So that's the repeating pattern is going to be, well, kind of repeating though. If you just look at this, 0, 1, 0, 1, minus 4, 1, 0, 1, 0. That is kind of the repeating pattern here in bands. Do the rest of them. So this is P6 for P7, 0, 0, 1, 2, 4, 5, 6, 7, 8, 9, for P8, 1, 5, 6, 7, 9, 9, 9, 0, 1, 2, 4, 5, 6, 7, 9. Then the rest of these zeros. If this was a larger system, it would have taken a while. You see a repeating pattern. So let me try to highlight the bands. We have this main diagonal. All of the fours. So that's just the point itself. Then we have the next band. It's 1, 1, 0, 1, 1, 0, 1, 1. The next band is zeros, last one, ones. Then you see it's metric. Repeating down here, 1, 1, 0, 1, 1, 0, 1, 1, down there. So is there a pattern here? Yes, there's a pattern. So we could, when we want to implement it, so for a larger one. So then you can actually construct this A matrix. Instead of just going through manually, you can construct it in a automatic fashion. Because you already know the diagonals, that's just going to be -4 bands, pattern here. This is for every for every length, -1, it's 0. Every length -1, it's going to be 0. And you see, if I had a 4 by 4 in the matrix, it would be 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. And then this one, this band is just going to be ones. I think. No, there's also going to be some holes. That might be the bug in my program. So, how can we solve this? Well, now we have a system A, X, B, or AP equals B. So you've already learned ways of solving this. So let's try implementing it. Can I remove this? Well, can I take down these lines here? Written in the matrix. Well, this loads, I can mention that the analytical solution for the system, that is u of x, y equals 400 xy. If that was it. Which you can use to benchmark. Okay, so let's see what I've tried to do here. So here I've done everything manually. So I've constructed B manually, and I'm trying to figure out a way to actually construct this A matrix in a good manner. Starting clearing, I'm just clearing all the old variables. I'm defining the number of inner nodes on the x-axis and y-axis. So n, that's 3, and m, that's also 3. And then I want to construct diagonals, my A matrix. I'm also going to. So the way I'm doing this here, by just looking at it, is that I see that this E is just going to be ones. So first I construct a vector of just ones, which is this. This part. Okay, so 3 times 3, that's 9. It's just ones. So that's going to be basis of all my diagonals. And then this D, here I'm trying to be clever and figure out which of them is supposed to be 0 for every n, 0. So 1, 1, 0. Then SPDX, that creates a sparse matrix where you only define the diagonals. So you have to look at this input and here. E, this is just ones. That is placed on -3, so that's -3 from the diagonal. I should probably. We'll skip back and forth. Okay. So this -3 here, it's easier. Okay, so maybe it's easier if I take 0. So 0, that's going to be the diagonal. So the diagonal here, it is -4, 4, 4, 4, 4, but I'm trying to be clever and only defining it below. That's why it's -2 times this one vector. That defines this here. So -2, -2. That's what's -2 times E at 0 from the diagonal. That is their diagonal. D with the holes in it I'm going to have at position -1 from the diagonal this. And the last one is -3, once down there. Okay, so now I've constructed half the matrix. If I take the matrix itself and add it to its transpose, I'll get this full matrix as a sparse matrix. And a sparse matrix takes less memory because you don't have to store the zeros. It's implicit that it's the zeros. It is also easy, or it's most probably also going to be faster to compute with it. Because you can do more assumptions. Okay, so then we have, oh, that's the wrong one. So then we have our A matrix. And I figure out the command to actually show the full matrix. So A, as you saw last time, is going to be stored in this weird format where only the position, so this is the coordinates 1, 1 is -4, 2, 2 is -4, and so on. If I want to see the full matrix, it's full A. And that is the matrix we just had. Okay, and then I'm just doing a direct solve. P equals A inverse times B. That's what you're doing here. And that works. Then you get this solution. So that's a very naive approach. You can also try to do some iterative. So initialization here is basically the same, only I define an error threshold and a maximum amount of iterations. The maximum amount of iterations is 1,000. Again, constructing A is the same way. The convergence, that's an old function, which is trying to look if it's diagonally dominant. And then we'll see if A is diagonally dominant. This is also available on Git. Want to play around with it. Then we can try to solve it using either Gauss-Seidel or Jacobi. So if I first want to try with Jacobi, and then we can see how many iterations. 108 iterations. We'll also take note that A is not strictly diagonally dominant. So convergence is not guaranteed till we manage to actually achieve convergence here. But it's not guaranteed. That doesn't mean that it will fail, it means that it may fail. In this case, it works. So that's good. Now we can see if title is any better. And it is. So here we only need, instead of 108 iterations, 55 iterations. But we can do even better, and that is with conjugate gradient. So I'm not sure how you implemented this. I've just used this. Bit late now. So yeah, conjugate gradient, as you've seen it before. Pretty straightforward. Here we only need 9 iterations. So that is 9. There's also one more trick we can do in order to decrease the number of iterations. And that is preconditioning. That is, we take a guess, maybe we do something with the guess, maybe it's based on something, and you will see that versions should be quicker. So when you do an iterative process, you need a starting point. Starting point, that's the precondition. So First one, the precondition was just zeros, was a place to start. So I just picked it randomly. But if let's go back here now. So now I'm running the Gauss-Seidel. Last time I ran the Gauss-Seidel, it took 55 iterations. So if I instead make this preconditioned P, just arbitrarily chosen 25 times 1, so I'm just guessing that all of these nodes here should be 25. And it's 5 less iterations. It's actually better. I just started somewhere else, basically. And the same get gradient might not be better though. So yeah, I need 2 fewer iterations. Problem with preconditioners, this is just arbitrarily picked. You can also do a lot of fancy stuff with preconditioners. So try to precondition it. We can see 50. You can also precondition it to be the exact solution, but then you've already solved the problem. 50 is apparently. A fourth way of solving it is to actually just run through all of the equations. Again, it is easier to set up, just doing it in a grid by grid basis. So here you see the nodes. I've just picked all of the nodes, so yeah, 5 by 5 instead of 3 by 3 because I have to calculate. Here's the boundary conditions, so the top part and the right part. And I start an iterative. If you first look at nested for loops, so what you're doing here now is basically solving this equation for every grid point. See, I'm looping over I from n minus 1, so that is basically these points here. Well, 1, 2, and 3 there, and also these here in j direction here. Basically, u of nu equals the all ones, and then hope for a stable. Again, if the update isn't much, then you stop. And you see you need many more iterations. 100 iterations. More formally, I am solving so in this last I'm kind of introducing third dimension. But as I say that u, I, j, k plus 1 equals the old ones. Fourth, or there, I plus 1 j, iteration k, j plus I minus 1 j, iteration k plus I j plus 1 iteration k plus I minus 1 iteration k. You can also solve it like this. So that's basically this equation up there. That's a very straightforward way of actually doing it. It's not as a very naive way of doing it, but it works. It works for ellipticals, and it also works for parabolic. So when you want to solve the wave equation, this is the easy way of doing it. Often how we do it. So I think there's questions. If not, then we can take a 15-minute break and start at 1:10. Then we'll talk about Neumann boundary conditions.